we mentioned some ideas, and now let us consider some further ideas, and that is how people looked at the hydrogen atom. With no equations nearly, and just what is the picture. So the hydrogen atom, as you know, you have a plus charge and you have an electron which is minus charge. So you can ask Newton, first of all, what is his opinion? He didn't know about the Coulomb interaction, but Newton was clever, very clever. So if you will come to Newton and you will tell him that there is an attraction between the electron and the proton, and the attraction goes in the potential like 1 over r, he would say, I know the solution of this problem. It's like gravity, exactly like gravity. Of course, you don't have masses, you have the charges of the electron, but it's the same thing. So in that sense, what Newton would say is you have some path of the electron like the moon around the earth or like the earth around the sun, some ellipse, and it's going like this. This is what, let's say, Coulomb thought. Newton didn't think about it because he didn't know about the electric interaction. But then there was a problem. Then there was another guy called Maxwell, and he solves the Maxwell equations. And from the Maxwell equations, there is a problem. What happens to this electron according to Newton's law? You know it is accelerating here. This is the centrifugal acceleration that you have. What happens to a charged particle that is accelerating? You know this from your antennas, from your cell phones, that you get all your information. If you have a charge which is accelerating, according to Maxwell equation, it will emit light. It will, emit radiation. What will happen to a charge that emits radiation if it's accelerating? It will lose its energy. So according to Maxwell equations, one can show that the particle will lose energy. Now that is very bad, because if you are built out of atoms, and atoms form molecules and they form eventually you, what if everything collapses? You would vanish. You would be of zero size, assuming that the proton is of zero size. But you know that of course the proton has a finite size, but of course the size of the atom is much bigger than the size of the proton. This is roughly 1 angstrom we know today, and the proton is much smaller. So there is a problem with Maxwell equation. So actually one reason why people liked quantum mechanics is that it solved this big problem of classical mechanics from the radiation. Now you would study, maybe part of you did not study electrodynamics. You would study radiation of accelerating bodies in a course maybe next semester. I don't know if you know about this in the detail, but you should know this general information. So, okay, Maxwell and Newton are most likely not correct. So then came Bohr. And what Bohr says is that you have some preferred orbits, that the particle can be either in this orbit or in that orbit or in that orbit. It cannot be in between. So this is how Bohr looked at the hydrogen atom. Here he's solving this problem in the sense that he's saying you can be either here or here. So if you lose energy, eventually you'll go to the lowest energy, which is actually this one circle, but you cannot go beyond. This is the quantization already. That's why it's called quantum mechanics, because we have quantization of paths. In Newton's worldview, all these ellipse paths are possible. How are they determined? In Newton's laws, by the initial condition. You can choose to be anywhere in between. So depending what is your initial energy, then you can be any ellipse here is possible. But Bohr says, okay, specific path, and that's why it doesn't collapse. And he does it by quantization of paths, by a rule that we'll soon study. But here, what does this mean? It means, let's say the electron is going around like this. At this stage, according to Bohr, the electron has a position and has a velocity. it's still paths. Here you have some velocity, you have some position. So this is eventually turned out to be wrong. This is the old quantum mechanics in a picture. It's wrong, but it has some element of truth in it. Then the Brownie might say something like this. You have the charge in the plus, and then, okay, you have some wave in some sense. Some wavy thing, okay? It was not very precise. We don't know what it means, but it's not a path, it's a wave. But he doesn't know exactly to interpret this. Then came Schrodinger. He thought about the electron like this. You have some, not, the electron is not a point particle in some sense. The electron is spread out all over the atom of the hydrogen atom, and this size is roughly 1 angstrom. So he says you don't have a point, you have some density. So according to Schrodinger, you have some density, and the density is psi squared. So what he's saying is, solve the Schrodinger equation for the potential of the hydrogen atom, find out what is psi squared absolute value is going to be the density of particles, so the particle is spread out. This we already saw in this two-slit experiment is half correct, because when you measure, you get a click. You can localize the position of the particle with this experiment where you have these, you got these clicks on this, in this experiment. If you add one electron, it will click here. So you can detect a position. So it's not a smeared density. So eventually what Bohr is saying is that you have here not a density of particles, but it's like a density, but it is a probability density. So this very simple system of an electron and a charged particle over these years goes through some evolution of thought, what people think about it, and it has changed until this current point of view of a probability density, which again we need to explain what exactly this means, is still with us till today. So in 1927 up to today, there were no big changes in this point of view. We can, of course, there are many insights on the details of what are the energy levels and things like that, but the general picture has not changed since then. So in the exercise, which we'll have tomorrow, you will be reminded or learn about Bohr's quantization rule. I'm not going to discuss it here, but roughly speaking, you can take, for example, the orbital angular momentum of this guy. You write it as a function of theta. You integrate the theta, and you say this is n, and n is a quantum number. The point here I want to emphasize is that this quantization of paths have in the mathematical rule h. So Bohr is taking the h from Planck and Einstein, adding this to this law that I'm not interpreting, to this quantization, and h appears in here. And what does he get out of this exercise that you will do tomorrow in your exercise? What does he get when he applies his rule?
Allowed radiuses.
Allowed radiuses, but also something which is great, but energy. And why is energy important to get? Because energy you can measure. The energy levels of the hydrogen atom. And he uses this quantization rule, and he gets exactly the energy level of the hydrogen atom. And it works fantastically well He can predict the energy levels with a simple rule. Wow, he's very happy. He thought, this is really kind of this is already a theory in the sense that it's not something specific like Einstein. Einstein says, h nu for the photon. Planck says, a specific experiment here. Every system that has some kinetic energy and has some potential energy, you can quantize its trajectories in principle in this rule, and you will get something that you can compare to experiment. So he did it for the hydrogen and it worked fine. What do you do if it works fine? You do nothing. But it turned out later, when people try to use this method to calculate things slightly more complicated than hydrogen atom, let's say helium, what happened? This quantization rule turned out to be wrong. Now, of course, when you have helium, is like you have two charges and two electrons. That is a very difficult problem also mathematically because you have interactions between the electrons. So it was not very obvious what is the problem. Why can't Bohr predict something more complicated? But eventually what happened was this young guy Schrodinger coming inside saying that this quantization rule, by chance, it worked fine for the hydrogen atom. But if you work with other systems, it will not work good. And that's why we forget about Bohr's old theory and we go to Schrodinger's new theory. New, I mean 1927. But this, the energy levels of the hydrogen atom are given by this rule. We will study this using the Schrodinger equation towards the end of the course. N is the quantum number, so N can be 1, 2, 3, blah, blah, blah. And R is called the Reedburn Constant. Reedburn was an experimentalist who lived before Bohr. He lived in the 19th century, not even in the 20th century. That for you is really a long time ago. And he simply measured these energy levels, and the energy levels of the hydrogen atom, En, which were measured long time ago. So what I'm doing here is I'm plotting the energy levels. And this curve, what is this curve? This is the Coulomb potential. So I add the Coulomb potential to say this is the energy levels of this guy. And it's given by R, and then you put in R equal N equal 1, and then you get some number, and then N equal 2, then you get slightly higher number, etc., and you have many energy levels. So the word quantum in quantum mechanics means several things. It means, first of all, quantization of energy. And that you know even because you have colors. Because you see your color coming out, it's a specific frequency relevant to a specific electronic transition. For example, when you go, if an electron will be excited to this state, it will go down here, it will emit light at this delta E. And then what is the frequency of light coming out? You know that, right? That was what Einstein told us, h times nu. So if I can calculate, this is the formula for the energy levels. I know the light, if you are here, it goes down to here. I can calculate the frequency of light coming. This is something I can measure, and then I can check what are the energy levels. So when you have this atom, of course, I think you know this, then you see certain frequencies coming out. These are not necessarily frequencies in the, you cannot always see them, right? They can be below the red or above the ultraviolet, but you can measure them, and you can measure the radiation, and it was known before Bohr that it goes like this, and he could calculate this, and actually they could measure this R, this Reedburn constant. What is this Reedburn constant? What is it? What is the number? It's a famous constant. What is this energy level here? You don't know? 13.6 electron volt. And this 13.6 electron volt, if you do the theory, I'm not doing the theory, this is equal to m. M is the mass of the electron, e to the power 4. One can show it, and we will show it towards the end of the semester. E is the charge of the electron, divided by 2 h bar to the power 2. Wow, this is a nice thing. Reedburn measured this guy. Now I can tell you exactly what it is. It is related to the mass, to the charge of the electron, and to this Planck's constant, which now appeared with Planck, of course. It appeared with Einstein. And now we are at Bohr, that is 1911. It appears in this formula for the frequencies coming out. And it works because of how do you get this h? It's coming from this h that you quantize these paths. Okay. So in principle we are happy, but Schrodinger is not happy because of reasons I told you before. So now we will go into the head of Mr. Schrodinger at last. Okay, so according to some legend that I once heard, and most likely it's wrong, but it's a nice story, there was some seminar going on in those days, I think in Copenhagen, because Bohr was living in Copenhagen. He was the big guy of the physics in those times. And there was a seminar or some conference, and then de Broglie said, okay, the particle, like an electron, has some wave properties, and he gave his beautiful formula. So some guy at the end of the corridor asked, if it has a wave character, what is the wave equation? That was a very simple question. If you have a wave, okay, what is the wave equation? And then Schrodinger said, that's a good question. I'll solve that question. What is the wave equation? So now you need to build the wave equation, because vaguely speaking at this time, particles are like waves. Okay, so let us build the wave equation. So he went for some vacation in the Alps, according to legend, with some lady which was not his wife. Okay, so Schrodinger's in Schrodinger's head. I'm guessing, I don't know what exactly went over there. So, okay, let us just write down what we know. We have some clever people around, so we have Einstein, for example. And Einstein tells us, okay, that the energy, in some sense, is equal to h nu. He said about photons, but now we accept duality, so maybe it also means something for particles. And this I can write also as h bar. I divide by 2 pi, and here I multiply. So this is frequency, this is angular frequency, yes? I think you all know this notation, right? This is, nu is 2 pi. 2 pi nu is equal omega. We will use omega and h bar and not h and nu. Okay? You know this. This is common also in China, this omega and h bar. This is well known, right? So this is the frequency of the wave, whatever that wave is. Okay, but I also will respect Newton, for example. He was also a kind of clever guy. And what did Newton tell us? That a particle, because so this is the wave. This is the wave. But it's also a particle. Oh, it's very complicated. What does it mean it's a particle? So what is the energy? You have energy. What is the energy of a particle? So what is the simplest thing to do when you have an energy of the particle? What does it mean? A free particle. Just some particle flowing around here. There's no forces at the beginning. What is the energy of the particle? According to Newtonian mechanics? What is it? P squared kinetic energy over 2m. M is the mass of the particle. And later on, I will add here plus some V of R. I'm working now in one dimension, so I am a simple guy. But let's think only about the kinetic energy. You have a particle here. No forces are this. Forces are complicated. I don't want to deal with them right now. Now there was another clever guy, and that was de Broglie, right? De Broglie said the following, that P is h bar k. Again, k is 2 pi over lambda. That is the wave number of the wave. So you have some wave, you have lambda, and then you have 2 pi over lambda is k, and h bar is this. This is what de Broglie told us. So, and of course, from wave mechanics, from waves, we know that k is 2 pi over lambda. That is just the definition of the relation between the wavelength and the wave vector, k. Okay, let us take these guys as an input for some theory. Now what can I do with this? I can play with this, of course. So let us look here. Okay, E is P squared over 2m. But what is P? It's h bar k. So I can plug it in here. And then I'll get this energy is related to k. But on the other hand, energy is also related to frequency. What do I get from that? What? Dispersion relation. So every wave, you know this from classical, every wave has a dispersion relation related between the frequency and the wavelength. And it's trivial here. Okay, let us write it. So we have, okay, E, that is from 2 plus 3 plus 1. 1, 2, 3. Okay, E equals to h bar squared k squared over 2m. That is equal h bar omega. That is Einstein. That is de Broglie with the definition of what is kinetic energy. Okay, great. I can cancel h with here. And then I get, as was told here in the front, that this is h k squared over 2m. This is a dispersion relation which is different than what you know from wave mechanics, right? From the wave equation of the light, the dispersion is linear. This is quadratic. Omega goes like k squared. But we got it immediately here. Now, okay, if you know the dispersion relation, now I can write a wave equation. So you see, in physics, you know the answer, then you write the equation. It's not like you write the equation, then you know the answer. It's the opposite. So let us write some wave. We need later to explain and understand what is this wave. And as I mentioned, Schrodinger did not really understand what this wave is, but he interpreted it wrongly. But let us assume there is a wave. Why there is a wave? Because of the experiments they show us. There's this wonderful interference experiments for these electrons. So there has to be some wave. Okay, let us assume there is a wave, and then we will pray that all this is correct. How do I write a wave equation? I will write it like this. A wave, I'm going to write like this. Omega k t. That is a particular type of wave. This is called a free wave, an extending wave from minus infinity to infinity This is a wave, as you know from wave mechanics, right? But, okay, the frequency here has this dispersion relation. Now, I'm going to write the equation for the wave. So to write an equation to the wave, what is a wave equation? The wave equation, you know, is the second derivative in space of some wave equal to the second derivative in time, and you have the speed of sound or speed of light, whatever, to make the units right? That is a wave equation. So a wave equation contains any derivatives in time and derivatives in space. Okay, we can take the derivatives in time and see what is equal here. So the spatial derivative, that is derivative with respect to x of this wave equation, I now take the second one. Of course, I assume Schrodinger first took the first one, checked the second one, the same with the time. He played it with this a little bit, but this is easy, and I'll take here the sign minus. So when I operate this on this particular wave, what do I get? I get ik and then another ik. So what do I get here? And I have a minus here. So here I get k squared psi. I will write now, I see this k squared. What does it remind me? It reminds me of this k squared. So let us look at this. Minus h bar 2m, second derivative in space of the wave, that is equal to h bar k squared 2m times the wave, right? Because this is the energy, and I just multiply this by h bar over 2m. This is the energy. Now I'll look at the temporal derivative. Temporal derivative, I mean derivative with respect to time. And then it's easy to say, I already multiply it, that the derivative with respect to time of psi, what will happen? I take the derivative with respect to time, I get minus I omega k. And I multiply by I, so minus I is the square root of minus 1. So I squared is minus 1, as you know. Yes? This is the symbol also in China, I. Yeah. Same, not J, not something else, because some I, the usual I from complex numbers. So, okay, so I have this I. Then I take the derivative. This is the equation. So I get here omega k times h bar times I. So I get h bar omega k psi. And that is, again, the energy. That is, this guy and this guy are the same, right? Because this is the energy, this is the same thing. That means I now use the dispersion relation. This is equal to h bar k squared over 2m psi. Here I use this guy. And this guy is the same as this guy. I have a wave equation. I'm famous. So I can summarize that for free particle, I get the following equation. That is, the second derivative in space of the wave is proportional to the first derivative in time. Why second and first? You now understand why, because that is because of the dispersion relation, because the second dispersion gives you the k squared and the first derivative gives you omega k, so you don't have like the wave equation which are the squared and also here something squared because there the dispersion was linear. Here the dispersion is non-linear, it's quadratic, so that's why you get here derivative and here derivative. But then you get, oh, this is awful. Why is it awful? Because what is psi? You have here an equation and you had to put inside I. We don't like this I at the beginning, and later on we love it. Why don't we love I? What does it mean on psi? It's complex. What does it mean at all? It's an equation with a complex, in the complex plane. And the solutions in general, not only for a wave function, are complex numbers. You have a real part to the wave function psi and an imaginary part for any initial condition. Let me state it a bit differently. Of course, here I started with a free wave. So of course it has a real part and an imaginary part from the beginning. So I can throw away, maybe you say, okay, I'll throw away the imaginary part. I'll just mean that the physical entity is the real part of this guy. But why, you can ask, okay, what did I do? I just took this solution, which I know from the de Broglie and Einstein, and put it into a wave. What did I benefit from this? Because I know that I started from solution, I got an equation. Why do I do this? Why is this worthwhile at all? Because this solution now you assume also will describe a superposition of many waves, a wave packet. That you start with a superposition of wave vector with some k and another one with a different wave, like you have in the wave equation. You can solve it for a free wave, but you can solve it also for superposition of many waves, right? You have some initial condition and it spreads, etc., right? Are you with me? Yeah. So the goal of Schrodinger now is, okay, I don't want to solve a free wave. I can start with some, let's say, Gaussian wave. But then he finds out immediately that the solutions from some initial real solution will evolve into something complex, which is not good. So psi itself has no real physical reality. You cannot measure this psi. He understands this. And you need to interpret what is this psi. So what did Schrodinger say? Schrodinger said, okay, I cannot measure psi, but I'm going to interpret psi squared as the density of the particle. And he thought of this as, instead of having an electron is not a point particle, it has some density, and this psi square is the density of the particle when you solve this equation. Psi squared is always real. So it's no problem in principle to measure this, and that is the quantity of interest. This eventually turned out to be wrong. It's not the density of the particle, it's the amplitude of the probability of finding the particle. But that was Bohr. So, okay. Now, that is one thing. So we understood that you need to look at psi squared, and we have to look for its meaning. But there's also something disturbing here. Let's say you want to calculate something like this. You have an electron around the charged particle. Let's say you want to calculate to solve the problem of the hydrogen atom. This is a free particle. The energy was just kinetic energy. There was no potential energy. So we have to add something. First of all, this is too easy in the sense that this is just de Broglie and Einstein in disguise. But we want to add also some potential. So you think about the particle, and it is moving inside some field. The field could be the field of the hydrogen, of the positive charge in the hydrogen atom. It can be an harmonic oscillator. The particle can be in a world, in a box. Many different potentials exist out there in nature. We will solve all of them like you did in classical mechanics. So there are many different potentials, but there is some potential V of x. So we wanted to add V of x to the equation. How do we do that? And here he had to play with things and essentially guess. So he first did the following. He rewrote this equation let us make it, let's rewrite this equation, because this is representing momentum, this is representing energy in some sense. So let us write it a bit differently. So first of all, I can do the following trick, which has some deep meaning, which will come later. I can define P. And P, I'll just write it, is minus H, minus I, H bar, D over dx. The hat is here, and this means that I represent P. P is momentum, but I represent physical reality like momentum, not by numbers. Like in classical mechanics, the momentum of the particle, okay, give me its mass, give me its velocity, that's its momentum. In quantum mechanics, the momentum is represented here by some operator. This is an operator, which I defined just now. The operator, each physical observable that you can think about in classical mechanics has an operator description in quantum mechanics. Position has an operator description in quantum mechanics. Momentum, this is the first guy. Energy has a momentum has an operator representation. Orbital momentum, the same. Everything has some operator acting with it, but for now we are just defining it in some sense. We will later see what is its meaning. And then I can look at this thing and I can say the following. I can say, what is P squared operator over 2n? This is mathematics. If I square this, I times I is minus. So I get here H bar over 2m, second derivative in space, which is exactly what you have here. So another way to write the Schrodinger equation is to write P squared over 2m, which is what it is. It's an energy, but this is an energy. This is kinetic energy, but what is it? It's the operator describing kinetic energy in quantum mechanics, P squared. P squared, you take the operator, you square it. Now, an operator always acts on something. It's not a number. It's acting on what? On psi. This is equal IH d dt, d over dt, psi.
There's a minus in the momentum operator, but after you, in the second. And then
Yeah.
okay.
I times I is minus. Yes, this is correct for a change, but thanks anyway. So you can write it suggestively like this, and now I'm writing, you understand that this guy and this guy is exactly the same thing. It's nothing new. But now I have here the energy. Now I'm going to write it in a different way. What is this thing? You have an operator here. I add the word F. F is for free particle only. This is not the most general H. H is the Hamiltonian. The Hamiltonian is the equivalent to the energy, but energy has a meaning of a number usually, while Hamilton has, in quantum mechanics at least, it will have a meaning of an operator. But it's the operator representing the energy. Now it's a bit you might be a little bit confused because you can measure energy levels, there's no problem. You can measure energy levels, but there is still some H which is describing, which is an operator, so I can add this hat. This hat says it's an operator, and it's a free particle. Okay, so it's P squared over 2m. So now I can write the Schrodinger equation in a form that maybe you are familiar with, but of course this is still only for the free particle, but the potential is 0. I can write the Schrodinger equation for the free particle IH d over dt psi. And this guy is the same. I just did some massage to the equation, some very simple transformations, some definitions, and I got the same thing. But now I have here energy. And you understand that actually this is also a representation of the energy operator. In what sense? When we had a free wave at least, what does this give you? IH dt of the wave. What did it give out? When you took the derivative of time of psi, what did you get out? You get out the frequency, right? Because when you take the time derivative, you get out the frequency, and then the frequency is multiplied by h. That's the energy. So this is, in some sense, also an operator, but it's in time, and this operator is the kinetic energy operator because there's no potential. Now, what we will do, or this is an assertion, Mr. Schrodinger comes and says, I want to write now more general Hamiltonian, not for a free particle, but for a particle that lives in some potential. Let's say now we are working in one dimension. I'll later explain how it works. So you have some kinetic energy, which is described by this operator, because momentum is described by operator. And now what will you do to get the energy? What do you need to add here? You will add the potential. Generally, the potential can depend on time also. But this is the Hamiltonian, so it combines of kinetic energy. But again, kinetic energy is now an operator. And this guy is the potential energy. Now, I cannot prove the Schrodinger equation. No one can prove the Schrodinger equation. I'm trying to explain why it is reasonable. But this is just a suggestion, of course. The historical fact is that with this equation, now only the work begins. Now we're going to solve the Schrodinger equation all along the semester. And then we can go check its predictions and compare to experiment. And believe me, it works. It works by comparison to experiment. But the fact that I kind of hand-waved here my arguments doesn't mean that this is not a proof. This is just a suggestion. What will be the equation to the most basic equation in physics in some sense? What is it in higher dimension? Well, it's very simple now. If we accept all of this, you need to write the Hamiltonian of the system, and that will be combined of kinetic energy, usually, plus potential energy. You will learn, or you have learned, or you learned about the Hamiltonian in analytical mechanics. Maybe some of you are still learning this topic, I don't know. But Hamiltonian formalism of classical mechanics is exactly the same like Newton's formalism. You can use this energy, which in classical mechanics is not an operator, but sum of two numbers, depending on the position, and which is a conserved quantity when the potential is independent of time and when the mass is independent of time. And you can derive from this Hamiltonian by Hamilton-Jacobi Equations, Newton's equation. It's like a formulation of... Who of you have heard about Hamilton-Jacobi? Did you hear about Hamilton-Jacobi? You don't know Hamilton-Jacobi. But okay, this is for you then the energy. I mentioned this because you have to possibly educate yourself a bit more. In Liebhoff, it's there. So you can use a Hamilton formalism of classical mechanics. You don't need it. What I'm trying to say here, who is Hamilton? He was some guy from the 19th century who discusses only classical mechanics. He had nothing to do with quantum mechanics. So you can, he just defined the potential energy plus the kinetic energy, and then he showed how to derive Newton's relations from this. But Hamilton himself, even though Hamilton is the word that you will hear the most in quantum mechanics, what is the Hamilton? Each system has a different Hamiltonian. He's not, the guy himself did nothing to help quantum mechanics. He helped classical mechanics. Okay, so how does this Schrodinger equation look in higher dimension? Let's say dimension 3. So in dimension 3, we will have p vector squared 2m plus v now of r, let's say, and t. This is simply the Hamiltonian of a particle in 3 dimensions in a potential that in principle R, I write it R, this could be x, y, z, or it could be presented in a spherical system, or it could be in a cylindrical system of coordinates. Whatever you want, you can choose depending on the symmetry of the problem. So this is the H. It operates on psi, which now is not a function of x and t, but now it's a function of r. So for example, x, y, z, and t. And here you have the same thing, du dt psi r t. So this is the Schrodinger equation for one particle in a potential in 3 dimensions. What is this p vector squared? Well, you have a p, an operator, let's say in Cartesian coordinates. You have an operator, in momentum in x direction is minus I h d over dx. You have a momentum in y direction. You have a momentum in z direction. So what is this p squared? What is it proportional to? When I take it squared, I get the second derivative of x plus the second derivative of y plus the second derivative of z. So this guy is equal to, another way to write this, h squared, the Laplacian 2m plus VRT psi RT IH psi RT. So this is another way to write it, where I use the Laplacian because p squared means px squared plus py squared plus pz squared. And that's why I get the h bar squared. So this is an equation in 3 dimensions. In principle, if I want to solve the hydrogen atom, what do I need to do now? What is this V? That is the potential that the electron feels in the hydrogen atom, which is the Coulomb potential. It will not depend on time. I have to solve this equation. I'll have the wave function. And then I know how the electron behaves in the hydrogen atom. We will not do that at the beginning of the course because this is a 3-dimensional equation. I mean, in the sense that the coordinates, they are 3-dimensional. So we will start with 1-dimensional problems at the beginning, which are much easier mathematically. But before doing that, what is the general idea of this adding potential? What did Schrodinger know? He knew that, for example, if you have an atom and you have some electrons surrounding it, the electrons are not spreading like free waves. They are localized, right? Otherwise, you had no hydrogen, and then you would not be there. There would be no atoms. There would be nothing. So it's not like a wave phenomena in the sense that a free wave spreads. This is, again, the problem of duality. So you need the potential. What is it doing? Is avoiding the spreading of the particles. So a free wave packet you have some wave packet and then it extends or it moves like a wave, is somehow localized. Why? Because of this potential that acts in atomic systems that avoids the spreading. And that is the attraction, for example, that you have in the hydrogen. So this guy, let's look at it in one dimension, minus h 2m d over dx squared, let's say plus v of x, some potential psi ih d over dt psi. So if v of x is a let's say a constant, this will, and you start with some packet in psi, it will spread and go to infinity, like a wave, like you have a solution of the wave equation. Of course, you have a different dispersion, but it will be the same thing. So if I have a constant, you have a propagation of wave. Spreading, the wave doesn't stay here, it spreads and goes to infinity. This is not good because the atoms have a finite size. So, but if I have something, let's say v of x, let's say it looks something like this. Here it's infinity, here it's infinity, and here it's 0. So that is a particle in a box. In classical mechanics, it will go inside here and it will bounce backward and forward. It will not go too far. Assume that when you have some electron, this will be the potential that is confining the particle. So you see, by adding here this potential, or it could be something less dramatic, maybe v of x, something like that. So what happens here? By adding this potential, whenever v of x is becoming very big, what will happen to the wave function, to the psi from this solution? Intuitively, what?
Blocked.
It will be blocked or it will go down. So the wave function here, of course, here it will be 0. So the wave function, we don't know how it will behave. It will be something. We have to solve it. It's complicated. We will do the math later. But the wave function is inside this thing. And here, it will be maybe something like this. But the further you go, when the potential goes up, the solution here, psi, has to go down. And then that is why it's reasonable to add to this kinetic energy that, again, you knew this from the free waves, from the free particle experiments, from de Broglie, you knew this kinetic energy, and now you add this guy. So this makes some sense. But like Bohr's theory, maybe it's correct, maybe it's not. Again, we have to solve it and see if it actually works in real experiments and real life. Of course, I would not be telling you all this unless I knew it was correct. So it's correct. Okay, good. So we have now a suggestion for quantum mechanics. Let me just summarize. So we have a quantization rule. For observables. We started this, but this will be general. And this I mean by P of x is minus IH d over dx. By quantization rule, I mean that observables, which were numbers, turn into operators. Operators. Operators are important in quantum mechanics. Of course, the Schrodinger equation describes some wave what does it mean? Okay, we'll have to study like later. And also dynamics of particle in a potential field. So it is this duality, which means it's both a particle and it is a wave, and now we have an equation that describes the wave. For a free particle, that is when the potential is zero, the Schrodinger equation is easily related to the works of Einstein, de Broglie. It just says that the equation didn't come out of the blue. It had a firm basis. The non-trivial part that Schrodinger did was that he added the potential. He went beyond the free particle. He was much more ambitious than just trying to describe a particle with no potential. He really wanted to describe everything that a force is acting on it. So he added this V. What was his next step? Someone has an idea? He solved, yeah.
Force without potential energy?
No, I say sometimes force, sometimes potential energy. The potential energy, in classical mechanics, the derivative, the del of this is the force. So I can say force, I can say potential. For me, it's the same thing.
Only force have a potential. Only.
Yeah. Right. Sure. But you're absolutely correct. So I'm talking about physical forces like the Coulomb potential, harmonic oscillator, etc. So there are limitations. You cannot put any potential here. This is actually a very good and deep question. I don't know if you meant it, but let's give you the credit. There is the question. Maybe I don't understand the question completely, but the question is, what is the relation also to classical mechanics? So here I have a V. The V is not any V. It is the same potential that you use in classical mechanics. So the program is the following. You first need to identify what are the forces. If you don't know the forces, then okay, go back home and do your homework. So you need to identify what are the forces. For example, the Coulomb force. The Coulomb force, or the harmonic force, or whatever force you want, you identify in the classical world, and then you put it in here, but you put its potential. Okay? So like in Newton's equation, when you want to solve Newton's equation, you cannot solve it generically. You need to know what is the force. You put in the force. You get. So the same thing. This is the same force that enters in Newton's laws. Okay?
What about magnetic field?
Magnetic field, that's really advanced. You will learn in quantum mechanics too. But magnetic field, you need to redefine this momentum. I'll just give you the answer and you can talk to me later. But the kinetic energy in magnetic field, either you know this or you don't, is given by something like this, where A is the vector potential. So you need to go back to Hamilton's equation, define exactly how do you get from Hamilton formalism of classical mechanics the Lorentz force in a particle in magnetic field, define the Hamiltonian, which is not trivial because you need to add the vector potential inside, and then you have the Hamiltonian, and then you quantize the Hamiltonian. So your question is excellent in the sense that already in classical mechanics, momentum can mean this generalized momentum. And this is actually the generalized momentum inside here. So you first need to know very, very well classical mechanics, and you need to know what is the classical Hamiltonian. And when you have magnetic field, it's not so trivial, you need to understand, but eventually you build an Hamiltonian, which is classical, which gives you the Newton's, the Lorentz laws, and then you create the Hamiltonian, and then you quantize it by taking this P as the operator I defined here, okay? But this will not be studied in this course. So if you want, the short answer is in this course, Quantum 1, we don't teach particle and magnetic field. If you're very interested, go to volume 2 of quantum mechanics of quantum energy, and there you will see it. It's very important, for example, for radiation and many things. Okay, so we have leaped forward. Okay, before next lesson, so I don't know where you can find this. You cannot find, I think. This is my idea of how to explain Schrodinger. But the historical part was given by Leboff, as I mentioned. So you can read Leboff for the history. That is chapter 2. And for the next lesson, you can read, for example, Quantum Energy, volume 1. You can read about Gaussian wave packets. So up to now, I described the free wave. The wave was EIKX minus omega KT. And a free wave, if you take the absolute value of that squared, which is the psi squared, is actually a constant. So it's a super boring wave. It is really meaningless. So we can start with some wave packet and then see how a particle propagates. This is under this convex, it is in quantum energy. In my version, page 61 to 66. Quantum energy volume 1, pages 236, at least in my edition, 237, something like that. General properties. Of the Schrodinger equation. For example, conservation of probability, superposition principle, Fourier transform, which you might know already, so then you don't need to read this. This will also be studied a little bit in the exercise. Quantum energy, this I can find, for example, in volume 2, appendix 1, page 1458. But of course, this is only because I was, when I wrote this, I just was lazy. I had quantum energy in front of me, so I took it from there. I could have taken it from another book. The Dirac delta function. Again, quantum energy, volume 2, appendix 2, page 1468. These are, and also Ehrenfest laws. These laws, Ehrenfest laws explains how from this equation can you get Newton's equation. These are the topics that you should read in the weekend or whenever you want for the next lessons. The idea of my course, hopefully for some of you, is that you just read and then you don't need me and then you don't need to come to the course. That will be great. The reason is very simple. You are now the second year or you are third year or whatever, doesn't matter so much, but you are approaching the end of the first degree. And after the first degree, okay, you study a little bit second degree, but eventually you reach some point in your life that there are no teachers. There are some books and then there are articles and no one is going to teach you anything. So you need to read. And if you don't know how to read, then you are done. You can go and work in some industry or something like that. So the only way, if you want to prepare yourself for second degree, or actually also if you go into industry, if you need to solve some problem, no one is going to tell you, there's no teachers, right? I mean, that's the real life. There's no teachers. You need to learn by yourself. How do you prepare yourself for that? You read now, and if you are able to read by yourself before the lesson, then you know what you understood, and then there's no teacher, and this is the way of real science and real life in general. So I really encourage you to read before you come to class, and then you can ask me the questions, and we can propagate. So, let me see, do I want to? Okay, I'll propagate a little bit more. Maybe this is also a summary. I want to explain again in detail what is the operational goal of someone who's doing quantum mechanics and classical physics. So again, we have let's say this Hamiltonian. I'm writing it in a slightly different way. This is the Laplacian. R is x, y, z, psi r, t, I h, d over dt, psi r t. I is square root of minus 1, h. H, what is the exact value of h is 10 to the minus 34, 1.023. Wait, I don't remember the next. 6, I don't remember. No, that's h bar. But that is a, okay, h bar is, you need to divide by 2 pi. Oh yeah, it's right in front of me. No, excuse me, this is, yeah, you're right, 1.054, 10 to the minus 34 joule per second. What I want to say here is that h bar has units. The units of h bar are energy times time. But it has also other units. What is energy times time? The units? No. Divided by time is a spect. What is that? What is the energy times times is also x times p. You actually saw it from the point of view of delta x times delta p is h bar. That's the same unit. And what is x times p? What is the units of another physical quantity? Orbital angular momentum has the same units. So this is also orbital angular units of. The square brackets here means units of. This is very important because when you solve some solution, you should always check its units. You check its units at the end of the day, and you see, you know, that your energy, for example, I gave you the Bohr energy R, Reedburn over n squared. You have to check that this is energy and not some stupid thing with just no units of energy. I hate when I see exams where you see at the end of the exam some formula and the formula doesn't have the right energies. At the end of the exam, you get some solution and okay, you made a mistake. If you locate your mistake and say, oh, this has not the right units, I give you some points. If you don't you don't even know that the units are wrong, then I will not give you anything. So please check your units. Unfortunately, this is very simple, basic thing that I'm sure you heard it before, but it's needed. It also means, for example, that angular momentum is measured in units of h bar. So the angular momentum will be eventually given by h bar. So what is classical mechanics? What is the program of classical mechanics? What do we do there, generally speaking? Classical mechanics. For one particle at least. We have Newton's law, V. And as I mentioned, this V and this V is the same. This potential is the same potential that enters in the Schrodinger equation. Now, how do you solve this in principle? No, we are not solving anything, don't worry. You solve it like this. You give, what do you give? What is the initial input to this usually, at least in high school? Yeah, you need to give the initial position and the initial velocity. Why do you need these two initial conditions? Where does it come from? It comes from the fact, the two dots. The two dots is the second derivative in time. So two dots is second derivative in time. So you give this, and then you get essentially r of t. And then you can plot some trajectory. This is a trajectory in 3 dimensions. That is the goal, to find this potential. You give me the field, and I will give you this trajectory. That's Newton's goal, at least. You can do this usually only with a computer, because if the potential is very complicated, you can do it only on a computer. In quantum mechanics, there is something which is a bit different compared to classical mechanics, which might be at the beginning surprising. What is the time derivative here? It's first order. IH bar d over dt in Schrodinger equation. So what are the initial conditions you need? If I want to get psi r of t, the initial conditions, because it's a first order in time, what are the initial conditions? You don't have two initial conditions, but you have a field. This is the initial conditions. You need to give me the state of the wave function, psi, at time t equals 0. If you give me this information, how the system is prepared initially, and you give me what is the potential V of r, in principle I can work hard and solve the Schrodinger equation and then get psi r on t. So here the input is much, what is this input here? The input here is in 3 dimensions, 3 positions, x, y, z, 3 velocities, 6 numbers. Here it's a whole function that you give as initial condition, and that's because we are looking for a solution which is a wave, so you need to give me the whole wave, and it's only the wave at time, this 0 means time t equals 0, and it's only this part because you have the first order derivative. You don't, if there would be second derivative in time, then you would add more initial conditions needed. So this is a good thing. As I mentioned, I mean, not a good thing, but if you want to solve the Schrodinger equation, you need this. Psi r and t generally has a real part plus I, an imaginary part of psi r and t. So this field, this wave, is composed of a real part and an imaginary part. Because of that, as I already mentioned, you cannot measure psi r and t. Psi r and t not directly measured, not directly measurable. In the sense that we do not measure complex quantities of a field. We don't measure this. And this leads to the suggestion that we need to interpret what is the meaning of all these wave functions. So the measurable thing is psi r and t, absolute value, and this is equal to the real part, psi r and t, squared, plus the imaginary part, psi r and t, squared. This is some function which is always positive. It might change in time, of course, and of course it also might change in space, but this is what you can measure. And this thing, we interpret it as the following. Psi, absolute value, d3r. This is the probability, and this is the basics of quantum mechanics, of finding the particle in r delta r at time t. So the program is the following. Give me the initial condition. Second step, of course, give me the potential. Without that, in principle, you cannot solve. Third step, solve Schrodinger equation. Final step, obtain psi squared at some time t. And then you need to interpret it as a probability density. So, while in classical mechanics, you solve Newton's equation. You get some r as a function of t. You immediately know what it means. Here, the difficult part is why is this a probability density, and what is this meaning of this probability density, and what is a probability density? For that, again, you need to read more, and we will discuss this more in the next lesson. But essentially, what we are doing here in quantum mechanics with the Schrodinger equation is the following. We are taking space, z, xy, and then I want to look at some position r in space. I create here some box. This box has a size of d3r, delta x, delta y, delta z, a small box. And inside here there is some value of psi r t. If I take this value of the psi I get after I solve the Schrodinger equation. If I know this, then I know what is the probability of finding the particle in this small box. Of course, I don't need to look only here. There is a small box. I can make the small box wherever I want in space. There is some probability of finding the particle here, some probability of finding the particle there, etc., etc. But eventually you get something which is a probability density, and that means what are the units of psi? What are the units? This is for units. in 1 dimension and in 3 dimension. So what is the units in 3 dimension? If this is a psi r and t times d3r, so what is the units of psi in 3 dimensions? What is it? This is a probability. The probability is dimensionless. You have some number which gives you, okay, here the probability of finding the particle in this box is 0.23. If the box is not infinitesimal, there's a finite probability to find it. So if this is a probability, psi squared times d3r, this has no units. And that means that psi squared in 3D has units of 1 over volume. And in 1D, what will be the units of psi squared? 1 over space, 1 over meter, if you want to measure in meter. So this is 1 over meter to the power 3. So depending on the dimension, psi has different units because it is a probability density and not a probability. It has some units. Not psi itself is a unit. Of course, from here you know the units of psi. So what is the unit of psi? You just take the square root of this, and here you take the square root of this, so it will be meter to the 3 over 2. So this, all this we will continue in the next lesson. So all I'm trying to say here is I very briefly introduce you to the probabilistic interpretation of what is psi. In next lesson we'll also discuss what is the meaning of this probability density. But this is the wave. The wave is a probability density. You take the square. You don't look at the amplitude. This is psi. Psi is sometimes called amplitude. Or probability amplitude. And psi squared is the probability density. If it's a probability density, what do you know about psi squared? You know something very general.
Must be 1 if you take it from...
If you integrate over it from minus infinity to plus infinity, the total probability of detecting the particle somewhere is 1. So the integral over psi squared d3r over whole volume of the universe is 1. Always, because it is a probability density. This we will study in next lesson. It's called the conservation of probability. The question is the following. Okay, we can start. So we mentioned initial condition psi r and 0. Not every initial condition is okay. What initial condition is okay? An initial condition where the square absolute value of the wave function, the integral over all space is 1. So you have to start in a normalized state. And then the Schrodinger equation will evolve you will conserve normalization. This we will see in next lesson. And then for every time t, you will have conservation of probability. So if you want to read further, you need to read more on conservation of probability and the normalization of the wave function. This is important. The wave functions are always normalized because they are probability densities or probability amplitudes. Okay, so for now we'll say goodbye, and I'll see you next week.